Welcome to the home of a new series. This series will be all about discussions that I have with guests about a variety of different topics, and these videos will be characterized by being much longer, more like a podcast, and very different to the shorter videos that I usually do, so less visuals and more talking and more discussing. In the first episode, I've had the privilege of talking to three members of the Structured Atom Model team. Ido, who many of you already know from his presentations from the Thunderbolts conference, Andreas and Jan. They are currently working hard on writing a book to help explain the structured atom model in great detail. In the first discussion with them, I wanted to talk about transmutation and how Sam can help explain what might be going on. This discussion will be split into two parts. In the first part, we will talk about transmutation in experiments and go into great depth on the Pons and Fleischman experiment, as well as discuss what they think might actually be happening in the SAFIRE experiment. In part 2, we will look at biological transmutation, but let's start with transmutations in experiments. What might be useful is if everyone just briefly introduces themselves so that we can put the name to the voice. So, Ido, if you'd like to start.
Hi everyone, Ido here.
And then Andreas.
Hi, this is Andreas.
And Jan.
Good morning, this is Jan.
Excellent. In past videos, I've looked at both biological transmutation and the transmutation that occurs in experiments. And I've seen a lot of people commenting on, the validity of some of those experiments and whether or not they did it right. And in particular, the Pons and Fleischman experiment. A lot of people pointing out that, they were discredited for their results. But I think that fundamentally misses the point of what they actually discovered and the subsequent, experiments that were carried out to try and verify it. The way they were looking for something that maybe something else was going on that caused it. So I would like to jump back to the whole Ponsman and Fleisch discussion and start with a question of why did they think that a nuclear reaction was happening?
Right. So I think Jan can speak to more details there in a moment, but specific to that question is that before they had a press conference in 1989, which is quite famous, where they announced the discovery of this cold fusion phenomenon to the world, is that 4 years before that they had an accident in their laboratory. And from the top of my mind, they had about 1 cubic centimeter palladium electrode, which after a long duration experiment over the weekend, I believe, exploded. And it exploded with such a force that it left a gap in a concrete floor and the lab table was pretty much pulverized, etc. Meaning that it convinced them that in their system, in their experimental setup, there was only one explanation for such an energetic release, which would be nuclear transmutations, i.e. fusion. So this is what convinced them to continue with this and that they could somehow harness the nuclear energy, if you will.
Yeah, they thought it was a nuclear reaction, not necessarily transmutations. At that time, nobody had an idea that that was going on. I'd like to share a book by Charles Baudet. It's called Excess Heat, and maybe I can share the screen.
Yep, take it away.
This is the book, and it's the best one that explains what happened late 1980s and the 90s following that. So here's the cover and the table of contents I'll show here. You see it has an introduction by David Nagel. So here you see what's called the meltdown out here. So that's a complete description of what happened there. And that is followed by the power burst. I want to show what actually went on in the experiment. Anyway, but you can see here, this is the horizontal axis, days of electrolysis. So that starts at day 54, so nothing happens for 54 days, and then suddenly something started showing up. Well, actually it was day 64, I believe, here, this little blip. And then suddenly for 3 days you had this heating effect. So the vertical scale is here centigrade goes from 36 to 54 degrees. So that's the excess heat, and this is the power that was shown at that time. So the question is, how does it happen that an experiment has been running for several weeks, nothing happens, and then after 6 or 7 weeks, 8 weeks actually, it starts working. And then it shuts down for an unknown reason. And that's the thing that I think needs to be addressed. And to me, that is the biggest enigma of LENR here, how this can happen.
So the question really, I mean, obviously they see the anomalous heating, and in their mind, the only way that they can explain it is a fusion reaction. That's sort of at the forefront of their mind. But we now think that it's due to transmutation. But the question is, how can transmutation explain this anomalous heating event?
Well, let me elaborate a little bit. So what we just saw is this period that nothing happens and then suddenly everything happens. So that points to a storage mechanism. What that here in this book says there, he knows of no nuclear effect that includes a storage mechanism. So to me, this means that it can't be a nuclear thing. So this must be electrical. And so this is what happens in the SAFIRE experiment. The nuclear reactions that undoubtedly happen are of the form of transmutations. That's what we think. But then you still have to explain how this energy gets stored. Or maybe it's the other way around. Energy gets stored first, then you get a breakdown, an electrical breakdown, followed by transmutations. So that whole sequence is very important to understand.
So in particular, in the experiment, they saw changes to the electrode. So what is the speculation? I mean, where do we think the transmutation is occurring? Is it solely on the electrode surface?
Yeah, it's on the metal surface. It doesn't have to be the electrode. In SAFIRE, we saw the breakdown of the melting or evaporation of the tungsten probe when it came very close to a double layer in one of the shells there that's shown in SAFIRE. It's the electric field that's the double layer of the shells, or the what do we call them?
If I can make an extra note there. In the original experiment, they were looking, of course, for an explanation. And since they were feeding this experiment from Pons and Fleischman with deuterium, right? And they went through, it's the heavy form of hydrogen, of course. And it goes through the metal, the palladium electrodes. Now, in their mind, and it still is the case, most people still think that it is a deuteron-deuteron fusion reaction creating helium-4, and that is responsible for the energy release, right? The exothermic reaction.
Yeah.
But what we are more and more convinced of is that it's not that reaction, although it may occur, the deuteron-deuteron to helium-4 reaction that may occur, but it seems to be predominantly reactions of transmutations, meaning the metal, a metal electrode, which is activated through, for example, loading up on hydrogen or deuterium, and then with the electricity, as Jan pointed out, which is like the stimulus or the trigger or the energy input, which we know very little of, I think. And that is, of course, the reason that transmutations can take place. And any transmutation is, at least any natural, normal occurring transmutation, is per definition exothermic. You can force endothermic reactions, but that's a different story here. So I think what is key to take away here is that we really believe that we are dealing with transmutations, usually of metals.
So just going back to the Pons and Fleischman, and in particular, Jan, what you said about loading up, the fact that essentially the data shows that there is some sort of energy store occurring. Now, from what you said, Ido, and from what you've said, Jan, are we therefore thinking that effectively there is like a depositing of some of these protons that are almost ready to be activated, and then at the trigger point it causes the transmutation to occur? So they're all there waiting for that moment of activation, maybe not be the right word, but the point at which all of a sudden the atoms can start rearranging themselves.
Right, so there are many explanations to what you're alluding to right now, mind you, many people looking at this phenomenon. But what is key to take away here again is that metals, especially palladium and such, are capable of loading into the metal electrode a tremendous amount of hydrogen, whether it's the normal hydrogen or the deuterium. And it can load it up. And there was not too long ago, just last year, in 2020, there was an article from NASA which talks about that effect. And they equate it to hot fusion, which most people know what that is, with big tokamak reactors. And they point out that, of course, in a metal lattice, which loads up with hydrogen, the density of that hydrogen is like 1 million times more than in the plasmas that they use in those big reactors that they're trying to build right now. So I'm not sure if that answers your question there, but I think this is important, that the hydrogen is kind of like prepared for any type of fusion reaction. So it needs a very low trigger, it seems.
But it has to happen in a plasma.
You mean the electrode has to be exposed to a plasma?
Yes, well, the hydrogen can be the plasma, of course. And again, there's so much detail that we do not know. This is maybe going there a bit too soon. But what we see is that normally you need something of a plasma, you need something of a metal, you need an electric input, and you need to have it all in the proper place at the right time. And that's a very delicate thing, it seems.
So these are taken by the SAFIRE team, of course, and as many as 7 different layers you can see here. And each layer has supposedly is an ion electron double layer. And one of these could be like manganese or one of the other things that they found in the chamber. So that occurs in these shells, in this plasma. So this is a plasma, and it starts out as these little anode tufts. So, but this is an excellent diagnostic tool to investigate these double layers. And what they showed that at the double layer, there's an enormously steep gradient of the electric field as you go from the outside in, and it can be megavolts per meter. So, and those are that's the electrical environment you need to break down to get an electrical discharge, like a little lightning. But it evaporates the metal.
But the Pons and Fleischman experiment was an electrolysis experiment, so not the same in terms of plasma and double layers.
Well, I mean, I'll show it here anyway, even if you don't want to show it in the book. So this is a cathode by SRI, Stanford Research Institute at the time, by Monsieur Boss. And so this is a video, and you see these little things scintillate all over the place. So to me, each one of these is a little plasmoid, okay? So imagine that these big ones scale down from this almost a foot diameter to like less than a millimeter, 1/10 of a millimeter diameter. Actually, less than that at the microscopic scale. So that's the model that I have in my mind of what's happening. And so it's happening here. You see infrared radiation. These things, they flicker all over the place. And each one of those is a little plasmoid that discharges because it gets too close to the metal. So it's a complicated thing. So
It does seem that, sorry for the interruption there, Jan, but it does seem that when people are looking at those electrodes in these experiments closer, through all kinds of optical devices and measuring equipment, that the transmutation tend to be surface or subsurface, if you will.
Yeah.
So more or less on the outside. So that is, of course, another big clue that exposure of a metal to a plasma, which is what you're still kind of doing with an electrolysis experiment, right? That seems to be the major thing here. So on the surface.
Yeah. So this is a SAFIRE quote here: "The prospect of understanding the plasma interaction with matter at the submicron to the angstrom level in trapped potential wells in the form of double layers would afford a host of new potential experiments for plasma scientists." So that's a quote from a paper early last year. And so it's
so in terms of the Pons and Fleischman, because obviously, you know, they saw the anomalous heating, but they did not find any of the products that you would expect from a fusion reaction. There was no helium. I'm not sure, did they ever analyze the cathode?
Yes, they did, and it was only done like a few years ago. And they found indeed nuclear transmutations on the Pons and Fleischman cathode.
So when you say nuclear transmutations, obviously you're assuming that, but effectively what they found was elements that were not present before the reaction.
Exactly, and it's somewhere in this paper, and I can't quite locate it here, but there's a quote by
Jean-Paul Biberian.
Biberian, yeah. So he gave a recent paper on that, and it's I think it's only 2 years old or so that they did that. But they found the similar products as other people like SAFIRE found in their cathodes. So it's pretty much widespread now.
Right, so that would indeed confirm the idea that transmutation was taking place in the Pons and Fleischman. But obviously, because they were never looking for it, you know, they were expecting the products of a fusion, and they couldn't find it. And no matter how many times they replicated the experiment, they never found the products that they expected, helium. So therefore, it was sort of labeled as a fraud.
If I can react to that one, maybe?
Yeah.
We say that we never found that, but if we take a closer look, that is an opinion, if you will.
Yeah.
And so a small anecdote there. Right after the original interview with Pons and Fleischman, the whole world, of course, was starting to pay attention, including big universities and research agencies and stuff. So the MIT, which is pretty renowned and famous, had a chief editor there, which was Eugene Mello. And that man was taking an interest as from his job, right? So the MIT started to do reproduction experiments to reproduce it. And Eugene Mello, being the chief editor there, got to look at all those reports and results and whatnot. And he started to see that his own MIT, and now this may sound like an accusation, but this is from Eugene, he pointed out that the MIT actually started to commit fraud, which is the term that he used, to diminish the results that they had, and to make sure that the results started to show that there was no excess heating effect or anything to that effect or transmutations. So it was done very sloppy, and even with their sloppy reproduction efforts, there were still some results that pointed towards a possible new nuclear effects, right? And still they committed fraud and made it appear as if there was nothing there, and the rest is history, as they say. So this Eugene Malov came out, became a whistleblower, started producing videos, interviews, created a magazine, Infinite Energy, I think is the one, I'm not sure there now, and became the biggest advocate for this because he was utterly convinced through his exposure to this material that there was something there. That was his conclusion.
But I don't think he ever saw the cathodes being transmuted.
I'm not sure if he ever knew that one. I think that was after his death because he died somewhere after the millennial change, 1 or 2 years after.
2004, I think, yeah.
Yeah, something to do with that.
But again, this book by Charles Baudet gives an exhaustive explanation of what they saw. Like 10 or 20 pages, maybe more than that, of this whole episode. And so if you really want to get into some detail there, you almost have to read a report like Baudet's or Crivet's book, Hacking the Atom is another one.
Okay.
Yeah, those are good books to read if anybody wants to catch up on this material very much.
Yeah.
Now, of course, they were not the only ones. They sort of started this whole process of looking at, I guess in the beginning, in the early stages, it was the production of energy, but later on, obviously, people became aware that it was actually causing new elements to be formed. So in particular, I've written down, we've got Muzuno, who detected, I think it was chromium, iron, manganese, and copper on the cathode. And again, the question is this again a similar process that we're seeing to what Pons and Fleischman were doing?
Yes. Muzuno has written a whole book on it also. Yeah, that Muzuno experiment actually was pretty dramatic. I think he spent like 3 days trying to extinguish an anomalous power burst, I think they call it, that generated 100 megajoules of energy in total. And so it's an unbelievable event. So he kept putting buckets of water, put the experimenters, which was a cell, an electrolytic cell, inside a bucket of water, but it kept evaporating day after day. I don't think he actually figured out exactly what was going on there either. If he wouldn't have had it in water, it would have blown up probably, just like the Fleischmann and Pons thing.
I would like to point out that at this stage, when we're looking at experiments, and as we go along, we'll see that more and more, I think, that there appears to be at least two things happening. One is the idea of transmutations, meaning an interaction of a hydrogen plus a metal transforming into usually the metal afterwards, right? So from a manganese to an iron, or from a sodium to magnesium, meaning going up or down in the periodic table one step, if you will, to the next element. However, as you pointed out, there was a detection in this particular Muzuno experiment of chromium, iron, manganese, copper, etc., and a few others probably. So that's too many elements, types of elements there, you could say, just to explain it through a single fusion step. So this is already a clue that there are at least two things happening, and what we at least think is happening there is that the fusion does take place with the hydrogen or the deuterium, transmuting into one heavier element. But we also see that there are heavier elements which start to disappear or become less abundant in the sample, and all kinds of a whole host of lighter elements start to appear in the results. So we think there is an actual fission or a breakdown of certain elements going on in these experiments as well. So, and those results seem to be very mixed. So it's very difficult for anybody in the world right now, especially without proper models, to really figure out what is going on. And I think that is the big issue right now in the world, right? What is going on? We are clueless almost.
So when you say proper model, you're referring to the model of the atom, because using the, I guess what you would call the mainstream version of the atom, it's difficult to explain how or why these changes could be occurring. It should be more random.
Right, without going in too much detail, the mainstream physics that we all exposed to, we all learn, it is almost inconceivable, right, that at that kind of temperature with that low energetic input, if you will, that any kind of transmutation could ever take place. So that is their official point of view, their standpoint. However, how long are we going to deny that if we look at experiments? And these are just a few examples that we're talking about, but there's a whole array of experiments that have been done, and many results are simply not to be, discarded. There's too much there. It's too clear cut, if you will. There is something going on, and transmutations are taking place. So the question is, of course, how do we do that? What mechanisms are involved, etc. I think it's a critical question. But yeah, mostly we are of the opinion, I would say, that it's not possible. But looking at the experiments, yes, it does happen.
Yeah, so I think the SAM model actually can explain how transmutations occur. Ido and Andreas have figured out how that could happen. And so that is a pretty convincing sequence that is laid out in our book. But there's another key things that are not understood, and that's why the reason why LENR is a 30-year-old mystery by now.
So I guess what we can say is that with the current understanding that we have of physics, of transmutations, of the nuclear models, and there are quite a few there, they never explain this. So we had, unfortunately, he passed away a few years ago as well, Norman Cook, who resided in Japan, who was a world-renowned figure in the cold fusion community. And he was developing his own model of an atomic nucleus, which was also a static structured atom, if you will, only a little bit different, less three-dimensional and more layered. So he had more layers of nucleons instead of more three-dimensional that we have. But that was one of the few critical differences. So he was working on that too, and he pointed out in a book that there are at least 30 models for the nucleus, for the atom out there, and none of them are capable of explaining a decent amount of phenomenon, or are contradicting itself sometimes, or are contradicting other models, and so none of them are complete. Now, before we are going to claim here that we have it all, that's not what we're saying, but we do claim that we have a base for a very sound and logical and explainable model for the nucleus, which seems to completely jive with what we know about the elements. And that is an amazing thing. That means that we get much, much more detail about the inner workings of an atom, of an element, of a nucleus. And we start to have much more detail about all the beta plus and the beta minus reactions, etc. And now we are much better armed of looking at the LENR field and trying to tackle it. And we believe that those first steps is what we are taking here carefully, if you will.
Transmutation is probably one of the hardest things to explain.
Yeah.
So I don't envy you to have to make a video on that.
Well, I mean, doing the dentist packing was a challenge. I mean, I think these are all pieces of a puzzle, and it's a question of understanding some of those mechanisms that, you know, and some things are still, you know, a mystery. And it's not that this explains everything. I think it gets us closer to something that helps us to get towards that understanding. But it might be useful for us to look at some examples. So I know that when we talked before, we looked at the Iwamura experiment, and the obviously, again, this is in my mind even more convincing experiments in this field, done on a larger scale, you know, more professional. But again, they were using like a substrate that they passed the material through, and they saw a slow change from on the I don't know what you'd call it, the film that they used. They saw a slow change from one element to another. So it might be useful for us to look at that so that we can start sort of explaining why it is that SAM helps us to actually understand why this is possible.
One example here is strontium-88 in this particular experiment that you pointed out, from Iwamura.
Yeah.
And strontium-88 is what they used. And strontium-88 is what we're showing here in the atom builder. That's our tool for all this development. And after a duration setup, loaded with extra deuterium, what they see, and what they claim at least, is that this strontium-88 adopted, I believe, what was it, 4 deuterons?
Yes.
4 deuterons, so in total 8 spheres that we see here, and ignore the colors for a moment. And then becoming a molybdenum 96, and which is of course heavier by 8 or 4 deuterons. Now, if we're looking at going to flip back and forth, if you will, so when we have the strontium-88 here and we flip it back and forth, we can clearly see what the differences are, of course, in the builder. And to point that out, on the left we see 2 extra, what we would call conventionally neutrons. Those yellow balls would be neutrons. We call them proton-electron pairs, but that's beside the point right now.
Yeah.
So they don't act in changing the element, just making it a heavier isotope. So let's just discount them for a moment. And the big change is the blue structure on the right. So one more time, from strontium-88 to the molybdenum 96, we see that there's another, what we call a carbon nuclet, is created there, and which is exactly the 4 deuteron difference in our count too. So what we see is a progressive buildup of the elements, which is of course the structured atom model. That is what this is all about. But what we can also see is that apparently, right, the strontium-88 can adopt extra deuterons on the right side here, and then transmutating to molybdenum. At least that is what the results tell us. Now, exactly how and why and how we trigger these kinds of reactions, that's a little bit different topic here.
Yeah.
But just looking at the transmutations, this is already what we can conclude here. That, yeah, this is how it works, and it seems to totally coincide with everything that we have.
It's probably very important to say here that, of course, we had created, Ido was doing that most of the time, those elements through special rules that are defined in the SAM model. And it is quite satisfying when you see that later on you come into see some experiment like this, and you see that it goes from strontium to molybdenum, and you can clearly make out what is the change, and it's very localized here, which gives us much confidence actually that this is what actually is going on. And on the other side, that the representation of the elements has some credence.
So if I can jump to a simpler example there for a moment, Gareth.
Yeah, no, absolutely.
A lot of the reactions we're talking about today is hydrogen fusion or proton capture, as we would like to call it, which is a common theme amongst many experiments. So just to point it out, we have a sodium-23 here. And as I stated before, the yellow ones are the neutrons, if you will. We call them still proton-electron pairs, PEPs. But if you look at a sodium-23, which is the standard only available natural occurring isotope of sodium, right? And it's part of table salt. Now nature apparently, and in experiments that we do, we give it one more proton or one more hydrogen, and then we reach the next element, in this case magnesium-24. And on the left side we see now another deuteron pair is created. So going back and forth, sodium-23 to magnesium, we see one deuteron pair extra created, which is of course one proton and one neutron in the conventional model. So what I'm trying to say here is, we can see that the sodium-23 in reality actually only needs one normal hydrogen added to the nucleus, regardless of how that happens, right?
Yeah.
And it will transmutate very neatly upwards to magnesium-24. So like Andreas said, those rules were created basically with the first 10 elements. And if you continue building all the elements, and at element 38 and 42, you find that all that logic, all those rules that we put in there, still works exactly and precisely with results from experiments such as Iwamura or SAFIRE. That is very satisfying.
Yeah.
Just to point out the easiness of how we can look at an atom and already predict, if you will, okay, we just need to add one hydrogen there and it will transmutate upwards. Again, the debate of how we do that, that's a bit different there.
Yeah, plus as well, to be able to predict what will be stable and what will not be stable.
Exactly. That's all in there.
Yeah.
Through the rules and the build-up.
Okay, you've mentioned it, so let's talk about SAFIRE. Probably the thing that most people are most excited about. So slightly different in terms of the way that the experiment is run. But again, they too saw an anomalous heating event, and obviously later analysis of the anode did reveal the presence of elements that supposedly were not there before the experiment. Now, can you run through, because I know you've done some sort of research on SAFIRE, but can you run through what you think might have happened with respect to the anode and the changes to the surface, and how this relates to the creation of new elements within the chamber?
The interesting point here is we all looked at presentations of SAFIRE, of the project over the years, and there was one special thing that was mentioned, and that was the tungsten probe incident. Basically, in 2017, it was then presented also in 2018, and what happened is that basically they vaporized tungsten probes more or less, and what was left seemed to be structurally changed, and there were indications of elements that were not there before. And then in 2019 they did another experiment, and they presented it at the Electric Universe conference in the UK in Bath, and that was very interesting. They didn't give all the details. They didn't mention what the anode was made of. They didn't spill the beans on all the elements that they found, but at least some of them. And what's very interesting is that there was mention of predominantly cerium and lanthanum, also barium, and other more smaller parts like titanium, like calcium, like sodium. And when we listened to that, Ido was there, I was there, when we listened to that, and a day later, it kind of made the connection basically to the tungsten incident from 1 or 2 years ago. And we looked at it under the assumption that the anode was at least made out of tungsten or laced with tungsten. That was the assumption that we made there. And from then we looked at how do we get from tungsten basically to those elements that they showed as being there, cerium, lanthanum. And what you can see here basically in the presentation is that there is a fractal structure of the nucleus, and it basically has a backbone. And what we think happens is, or what happened is that some of the branches that you see here on tungsten were removed from the nucleus, and those are of course the parts we find, and the smaller parts, and the bigger part basically is this backbone, what is left over, and that is cerium, lanthanum, barium. So in essence, what we think happened in SAFIRE, in this special case, is that they pushed hydrogen through the anode, and that hydrogen, of course, was then ionized, and the protons reacted with the tungsten in the anode. We have a small, short fusion event. That proton, or maybe also deuterium, is attached to the tungsten, and it becomes unstable, and then it fissions. It really fissions like uranium. And that is then, of course, what we see as the results. And, of course, also what we see as the excess heat that they recorded. And that was quite a lot. And by our calculation, we think that the excess heat is in the range of 80 MeV per atom. You can compare that to uranium fission, that is around 170 MeV in the initial step, and it goes up to 200 MeV. So this was quite and really an interesting thing, and is kind of really strange thing if you think about that you would be able in this environment, in this heavily electrical environment, you would be able to fission a metal, a stable metal, into smaller components. But from all we can see, this is what happened. Of course, all is based on the assumption that the anode was made out of tungsten, and we basically 2 days after Monty Childs presented the results of the 2019 experiments in Bath, we gave basically a small little presentation at the second part of the conference at Pepper Hill Barn, where we talked about our assumption and what we think happened there. Later on, through some leaks, it became clear that our assumption probably was really right. The anode was made out of tungsten, so we were right in that regard. But we based it back then, we based it basically on the assumption that they continued the tungsten probe experiment. We might have given them too much credit there. To us, it seemed a logical conclusion to do that, but maybe it was just they used a heavy metal basically as anode, and it turned out to be tungsten.
Right, so if they'd have used a lighter metal, then you wouldn't necessarily see this because there aren't those branches to break off. You can't release the energy from the fissioning in that process. That's
exactly. We might have seen other reactions, smaller reactions.
Smaller, yeah.
Not that much excess heat, but not what we saw here in this experiment. That was quite unique.
That's fundamentally something quite revolutionary, because essentially what you are saying is this is a fissioning reaction or a release of fissioning energy with a material that is not considered to be fissionable, not radioactive. So essentially you're doing like a uranium style reaction with tungsten.
Yeah,
Right.
Probably we should have a look at uranium.
Yeah.
Yeah, well, I can do
compared
that.
to tungsten.
If I can make just a short comment in between there. Andreas already mentioned the proton capture, right, as a triggering mechanism, if you will. And if you go from a tungsten and you add a proton or a hydrogen, it should, predictable, become a rhenium, the next element. However, while I'm showing that here, I hope it's visible still, there's quite a structural change to the next element. So the nucleus has to keep creating those carbon groupings, those blue ones. And the purple is almost blue. And we can see that there's a big step here. And every now and then in the growth of the elements that needs to happen. So there's a big change there. So the normal transmutation step that you would expect without the detail, you would say, well, why doesn't the tungsten become a rhenium? But the lightest tungsten isotope is already much lighter than the lightest rhenium isotope. It's 5 different. So there's something going on here which normal physics or chemistry cannot really explain, why there's a jump of 5. So what we see is that the normal fusion step, transmutating to the next heavier elements, is resisted by the nucleus. It cannot do it unless it has enough of those. So it means it needs to load up on quite a few neutrons, if you will, before it can make that step. So the fusion step, we speculate, misfires. As a result, you get a fission reaction. But another experiment, if I may say so, Gareth, I know you have that one ready too, is that foil experiment, that explosive foil experiment with an electric discharge.
Yeah.
What we see there, it's pretty raw and pretty simple as an experimental setup, that is. And we see a host of lighter elements appearing. Predominantly lighter elements.
Yeah, so that was titanium. It might be useful if you can bring up titanium.
Well, titanium is quite light. Let me find it for a moment there. And then we'll go to uranium in a moment. But apparently, if you have a strong enough electric discharge, and the details of those experiments escape me right now what they used there, but it was a forcible discharge, right?
Yeah, they called it explosive.
Yeah, so apparently it's able to disintegrate atoms. Apparently, that is at least the conclusion we have to draw here, by lack of other explanations at all. But this is what happens. We see that happening in those experiments. You have element A, and then afterwards you have element B, C, D, E, F, and there tend to be lighter elements. Not always, like I said, there seems to be fusion and fission going on at the same time in many of these experiments. But all I'm pointing out is that regardless of the triggering mechanisms, and there are a few here, and there are differences between the tungsten and the uranium, which is where I will go now. So,
but by the way, silver should be also included that as a possibility.
Yes, silver would be fissionable in this line of thinking still. So what Gareth just summarized is that apparently, and this is a conclusion that we draw right now based on all that we know and see, is that yes, apparently electricity under the right circumstances can fission stable, non-radioactive metals as long as it's a little bit above iron, meaning there's energy to be released there, right? So this is the tungsten, and then we go to the uranium, which we have here. This is quite a large chunk of nucleons together, protons we call them always, no more neutrons. And what we speculate with uranium, or hypothesize, is that one neutron, or a proton, would end up here in the center somewhere, and we can see those green in the center almost touching each other there. Now, you could say this is too close for comfort without going in all the nitty-gritty detail here, and it would take an hour to just get here to understand it, but we can see they are too close for comfort. Normally, all the branches are separated by more space. And this is the natural limitation of the elements, meaning the more we load up, it wants to construct a new carbon nuclide here, but it cannot because the branches start to collide or overgrow in each other, overlap each other. The moment that that happens is the moment that a nucleus disintegrates into two lighter elements. And those two lighter elements tend to be, again, the barium, cerium, cesium, lanthanum, and a lighter component. Not sure where to go from here, Gareth.
Yeah, I mean, the point here is basically a little bit of history when this was, when they discovered fission in the end of 1938 and beginning of 1939. It was a group led by Otto Hahn, Lise Meitner, a guy called Strassmann, I think, and somebody else, Frisch, I think. What happened basically is they all expected that adding a neutron to uranium would give you transuranic elements. The idea that something like fission could happen was completely inconceivable. They even gave names to and atomic numbers and to what they found as results of the reaction, and they were all in the transuranic range. And then they kept on researching this and analyzing the results. And at some point in December 38 or January then 39, they had to give in, and because something that looks like, behaves like barium, reacts like barium, might actually be barium. And so they then came to the conclusion that actually the nucleus here had fissioned. And what is very interesting here, if you look at that, what they detected was as bigger part of the nucleus, that what they found was barium, lanthanum, cerium. Where did we find this before? The answer, of course, is SAFIRE. So if you look here, actually what happens, the model explains it very neatly. As I said before, you have this backbone structure, which is basically something like cerium, like barium, like lanthanides, and you have those branches that are breaking off and in case of uranium probably fuse again because they are so close together, while with tungsten they most likely do not fuse and we get the smaller parts. But what happens is that we can see in the model a clear structure of how heavy those basically fission elements and the fission parts should be. And the interesting thing is, and probably that is something that Jan can talk about here, that is that this is actually an enigma with current science, the asymmetric breakup of the nucleus.
So, if I can pick up the ball there, here we see that asymmetric breakup, two bumps or two hills, two peaks, and this number here reflects the number of protons that we see in the builder, the number of spheres, right? And it's 130 to 140, which would be the products like the barium, cerium, lanthanum. And that's that elongated structure, the backbone that remains, if you will. And the 90 to 100 is the collection of those branches breaking off. So if we have the branches breaking off, I need to go back there. If we have the branches breaking off of a uranium, you're left with something akin to a cerium, for example. So just to show that is if we can, what we can do in this builder is we can take a whole branch there and we can take it off, if you will, And we also see in this thing, we see the number there like 52. So I already know the broken off part is 52. So simply deduct it from uranium, you're left with the total. This is how we can do it and calculate it and show that that's how it's working. And if you do these numbers and you break off a couple of those outer branches, you end up exactly with these peaks here. So just break off the branches, keep the barium, which needs to resettle a little bit through beta decays, which is a known fact. And the remainder broken off branches form exactly that number. So what we are saying is from the SAM model, it automatically follows that you have this double peak here in a fission reaction. In contrast to any and all other models, they are all explaining, in essence, an even splitting there, because they make no difference, they have no structure in the nucleus, it's just a collection of protons, neutrons, etc. in a chaotic sphere or something akin. So this model shows that this double peak that we witness in any type of fission reaction is always taking place, including with a tungsten, for example. You again get those barium, cerium, lanthanum regions and smaller products again.
It just flabbergasts me that when we look at this and, you know, talking about effectively tungsten fissioning and releasing energy, that the question then becomes, why are we the only ones that are talking about this? Why is this not something that is being shouted? I mean, obviously, the only way you can explain it is using this model.
But the thing is, what we discovered, if you will, through the structure and much more, which will be in an upcoming book, if you will, is that uranium, as we know, is quite unstable. We call it radioactive, meaning they tend to decay quite rapidly. And you only have to add a slow fermic neutron, meaning a very slow neutron, to it, and it starts to fission and release a whole bunch of energy. So why are the other metals, are we not talking about that? Well, they are much more resistant to this. Just adding a neutron there will not do it. But an electric discharge, in contrast, apparently will do it. However, the current models state, you know, that's not enough to do nuclear transmutations. But if we're looking at all these experiments, one has to come to the conclusion that's exactly what's taking place. So why are we not talking about it? Well, the normal metals, the stable metals, are much more resistant to this. Although we know that they can transmutate also, of course. There's a whole body of science out there doing all kinds of transmutations with particle accelerators.
Yeah, but I think even if you look at SAFIRE, you know, they I don't think they directly talk about it, but they do suggest that it's fusion, not fission.
I'm not sure what their standpoint is, or their official standpoint. I think they're considering all options, probably, right? Trying not to go too much one way.
Yeah.
On the other hand, what they're also stating, at least publicly, is that they're going to try and make solutions for nuclear remediation, meaning burning up the nuclear waste and whatnot, and in the process maybe even create energy. So I think they're contemplating this view. I'm not sure if they adopted it, if you will. I don't know.
Yeah. One other question before we move on from SAFIRE. In the experiments, they talk about a catalyst, which they sort of hint is some sort of gas that they put into the chamber. And when they change the mixture, the whole process stops. And then when they add different mixtures, you know, it sort of flared up. How would you see that being explained in this model?
Well, Jan already pointed out the importance of the electric environment and how that is constructed, right? I.e. the double layers, etc. So that's a critical factor there. So on the other hand, what they've been playing with is that catalyst that you mentioned, and I think they're referring to the atmospheric gases there.
Yes, I believe so.
I.e. nitrogen and such. And when they introduced oxygen, I believe, the whole process got killed. It stopped, if you will. Now, when just looking at oxygen and nitrogen as gaseous molecules, right? They have the electron affinity, meaning how easily they adopt another electron in a plasma environment, right? A charged environment here. The nitrogen resists it, meaning it wouldn't want to take up another electron, so it's resisting that. So that's what we speculate or hypothesize again is contributing to the creation or of the ease of the creation of those double layers, if you have the right gases there. If you introduce, however, an oxygen, even in the form of O2, and you start ionizing it, like in a fluorescent light bulb, which in principle is not so different from sapphire, those oxygens are very much electroaffinity, have high electroaffinity, meaning they do adopt electrons, and if they encounter those protons, those stripped protons, if you will, then, of course, they will connect very readily, meaning the hydrogen, positive, plus the oxygen, which is now became negative in that environment, they will readily fuse together in a chemical sense, right? And create H2O. So taking away all your ionized molecules and atoms there, you're killing your electric environment, or at least the prerequisites of it, if you will. And therefore you stop your process.
Right. So it's not really that you're stopping the transmutation, you're stopping the electric flow, which is the trigger for causing it. Yeah, that makes
at least that's what we think. Yeah, more or less.
Yeah. Okay.
So we're not sure if that, and mind you, there's a lot of detail that we do not know about sapphire, right? We have to go on what's presented in public arena as anybody else. But that's what we think, and it seems that the catalyst, right, that it's critical in keeping and creating and keeping that electric environment, such as double layers. So you have this huge magnetic field difference or voltage difference, right, in order to trigger this. Otherwise, it doesn't work. But they would be more knowledgeable here, for sure.